All right, so let's start with number 3. That's this one. The thing is 2 meters long, so this distance is 1 meter. This distance is 1 meter. And this is half a meter. And first we have to calculate the external loads. So free body diagram of the whole thing. We have a point force at the middle that we don't know. I'll call that RB. We have a couple going this way of 1,500 Newton meters. Here we have a downward force of 2,000 newtons. A pin joint applies a full force vector, so I'll call that RA. And then we have this compressive force here of 5,000 and a couple in this direction of 3,000 Newton meters. Anyone know how many Newton meters you can apply with a screwdriver? Like order of magnitude, what?
Like 15.
Yeah, that's right in the right ballpark, I think, depending on how much you struggle, you know.
I could draw 100.
We should have like Deform games at the end of this. And
Well, I mean, how big is a screwdriver? Yeah, I mean, if you make a big enough screwdriver, you can put even more force on that thing.
like more to grip.
Like that.
If you put handles on it.
Like your whole body just wrenches around.
Yeah. I'm not picturing a screwdriver like that, though. Okay, anyways, yeah, I was going to say 10 Newton meters. So these are big. Like, you couldn't apply that couple with a screwdriver. Not even the one you're imagining. Okay, so Newton's second law says RAX, RAY plus 0, negative 2,000 plus 0 RB plus negative 5,000, 0. 1, 2, 3, 4. Okay, that's everything is equal to zeros. How come I'm not putting the couples in there? Because couples are, the definition of a couple is a pair of equal and opposite forces. So the forces always cancel out and all you're left with is a pure moment. Okay, so RAX is positive 5,000. And then we have the second equation that we can't solve yet. RAY plus RB is equal to 2,000. I'll set that aside. And then we'll go to the moment equation. And I'll put my about point here. Well, I guess let's do the X moments first. These are all couples. They always have to just be adding up couples and setting the sum equal to 0 because the nature of these drawings is you can't tell, like, I mean, really, I could draw it from another direction and show how offset it is from the center, and then you'd have to calculate those moments and stuff. But the way you'll always see these is just as couples applied along the axis. Okay, so what do we have along X? We have positive 1,500. Oh, I forgot something. So this hinge here also has to restrict rotation about the axis, and so there's going to be there's going to be this force here like this, but there's also going to be a couple, I'll call that torque, R, reaction torque, something like that. Okay? So now we have fancy TR plus 1500 minus 3000 is equal to 0. And so TR is equal to positive 1500 Newton meters. And now the Z equation. The forces acting at the about point don't produce a moment about that point. The 2000 does. It has a moment arm of 0.5 meter. So I'm going to write this as plus or minus 0.5 times 2000. And would that make it rotate clockwise or counterclockwise around the about point? Clockwise. So that's going to be the negative. And then the RB has a moment arm of 1. And would that, a force in that drawn direction, make it rotate clockwise or counterclockwise? Counter. Did he say counter before?
Yeah.
Okay. I couldn't hear. I was like, I'll give him the benefit of the doubt. And then, okay. And nothing else will produce moments because that 5,000 has its line of action go right through that. So this is equal to 0. So we have RB is equal to positive 1,000. And now we can go back to this starred one, 1,000. So RAY is also 1,000. Okay, so we have this force RA that's equal to 5,000, 1,000. This force RB is 1,000, acting in the direction I drew in the free body diagram. And this reaction torque is 1,500. Okay, so now let's draw this thing out. So over here we have this force of 5,000, 1,000. We have a torque going this way of 1,500. I usually write the Newton meters in just so I don't accidentally treat that like a force. Then we have a 2,000 Newton, well, let me draw the midpoint, is like here. So the 2,000 Newton force going down is there. We have a 1,500 Newton meter torque. And an upward force of 1,000. And then at the end, we have 5,000 newtons. And 3,000 Newton meters. So now we're ready to start the internal load stuff. we need to figure out how many cuts we're going to make. So let's identify all the points where things change. So we got the two endpoints, the midpoint, and the midpoint of the midpoint. And so we have like an n equals 4, and so we know we're going to have to make 3 cuts. Okay? And so what are the cuts? Cut 1 is going to be for x's between 0 and 0.5. And so let's draw that. And so we haven't gotten to that quarter point yet. Darn it. So that's not going to be included in our body. We haven't gotten to the midpoint. God damn it. Okay, so the midpoint is like here, so the quarter is like here, and we haven't gotten to that. So the only stuff that's going to be included on this is the stuff going on over here. And then cut 2 is going to be for x values between 0.5 and 1. So that is going to be, okay, so this time we're going to be including the stuff at that end. We're going to be including the stuff a quarter of the way along the length. But we won't be including stuff at the midpoint or at the right end. And then for cut 3, this is for x values from 1 to 2. This time, we're going to be including stuff at the left end, at that quarter spot, and at the midpoint. But we won't be including stuff at the right end. Okay? And the most common thing for people to get confused about is they look at these boundaries and they're like, wait a second, like let's look at cut 2. It says that this only includes from 0.5 to 1. So why are we including all this stuff before you get to x equals 0.5? Well, remember that the cuts we're taking a body that always goes all the way from the left, and it goes to an x value on the right. So we're always including everything that happens on the left. That x value just tells you what are the possible values of x that define the right end. Yep.
I guess it's something I never really got from statics. What makes us choose like which side to start from and progress along?
Yeah, nothing. I mean, just me, because I'm just doing all my examples that way, and I think you should do all of your examples that way too. If there's ever a time that it really makes it more difficult to go from the left, then get up out of your chair. You can imagine doing this though, and walk to the other side of the beam, and then draw it that way and do it like that.
Okay.
But I just always do it from the left, and I think since I always do it from the left, I think you should too. But if you did it from the right, you would get the same thing. It's just if you go back and forth, you're going to make algebra mistakes.
Yeah, well, I'm just thinking like in terms of you want to start, like you usually almost always want to start with like your fixed point, like your pin and your hinge or whatever, or does it really matter?
Oh, as an about point?
Yeah, I guess.
Okay, as an about point, I always, on that the math is always going to be easier if you choose the far left endpoint as your about point for the cuts.
Okay.
So that's what we'll always do. Because otherwise, like the one variable is x. And so you want that x to represent your moment arm.
Okay.
And if you don't choose the far left as your about point, then that doesn't happen and the algebra gets messy.
Okay.
All right. So now, I don't know, hopefully this drawing sort of helps you see what's going to be included in these cuts. So let's go to the cuts now. So first cut 1, this is for x values between 0 and 0.5. So we'll draw a representative piece, and it includes everything that happens at the left endpoint. So we have this force vector. And what was that couple? 1500. And you can see from this drawing of cut 1 that we haven't gotten to the 2000 Newton force down yet. And so the only other stuff going on is going to be the internal loads. So Newton's second law says 5,000, 1,000 plus T0 plus 0 negative V is equal to zeros. And so on this piece, the tension is negative 5,000. The shear force is positive 1,000. So based on that tension value, is this in tension or compression? Compression, yep. Positive is tension, negative is compression. And now we'll go to the x moment equation. And this says positive 1500 plus the internal torque is 0. So that internal torque is negative 1500. And for the z moment equation, that's going to be our about point always. And so the 500 and 1,000 don't do anything. The only thing that causes moments about the z-axis is the bending moment. And then a clockwise moment of v times x. This is x. And our v is 1,000, so this says m is equal to 1,000 x. Any questions about the first cut? And then the second cut, was that Joy? She better come in here. Hey, Joy. Okay, now cut 2. This is for x's between 0.5 and 1. So this time we have our forces here. We have our reaction torque of 1500. And this time we have a downward force of 2000. You can see that in this picture of cut 2 that we've made it, that's included now in our body. And then we have the internal loads. No, fancy T. So Newton's second law says 5,000, 1,000 plus 0, negative 2,000 plus T0, 0, negative V. I'll just write it like this. Add those two vectors together. Is equal to zeros. And so T is equal to negative 5,000. V is equal to negative 1,000. Question? No, that's a couple. I would have to, but that's a couple. Okay, so now we'll do the moment equation about the x-axis. So we have the 1,500 and the internal torque. And so we get an internal torque of negative 1,500. Same as we did before. And now the z moment, the about point is going to be here. And so we have a clockwise moment of 2,000 times a moment arm of 0.5. So that's negative 0.5 times 2,000. Plus m minus Vx is equal to 0. You always, on every single cut, you have a plus m minus Vx at the end of everything. And so we got m is equal to 1,000 plus Vx. And so m is equal to, I'll write it as negative 1,000x plus 1,000. Any questions about cut 2? And then cut 3. This is for x values from 1 to 2. And you can see from our picture of cut 3 before, it's going to include the stuff at the left end, that downward 2,000 Newton force, and then the roller and the torque that happened at the midpoint. But it's not going to include the stuff at the right end point. Okay, so at the roller, we got that from the external loads here, 1,000. And we had a torque going this way of 1,500. And then the internal loads And when we get to the Z moment, we're gonna do calculate our moments about the left end. You're right. Thank you. So that would be here, downwards 2,000. Yep. So Newton's second law says 5,000, 1,000, plus 0, negative 2,000, plus 0, positive 1,000, plus t, negative v, is equal to zeros. So t is negative 5,000. V is 0. Then the moment equation about the x-axis. We have positive 1,500 plus another 1,500 plus the internal torque is equal to 0. And so the internal torque is equal to negative 3,000. And then the moment equation about the z-axis. Nothing from the stuff at the left end. We have negative 0.5 times 2,000. So negative 1,000. Then we have a counterclockwise moment of 1,000 times 1. And then we have plus m minus vx is equal to 0. These cancel. And so m is equal to vx. V is 0, so m is 0. And if you wanted to visualize this, you could graph it on Desmos or whatever. I mean, there's not too much value in getting good at graphing stuff on your own, I don't think. But if you wanted to look at that, you could on Excel or whatever. Any questions about that? Okay. So the next, any other homework questions you want to see?
I had a question on
Yeah.
number 4.
Yeah.
Vessels, but
Oh, pressure vessels, that's right.
Start it because I'm not really sure how you go from a weight strength back to the wall thickness.
Okay. Let me just look at it real quick. Okay, so you know the size of the pressure vessel and you know the pressure. So you can calculate a maximum shear stress with the only variable being the wall thickness, right?
Yeah.
You got to that point?
Yeah.
Okay, and then from there, So,
We were given the shear strain,
right,
so I was confused where you put that in your matrix.
yes. Okay, so you have like this. Let's just say that it's uh, a function of the thickness, right? This is the thickness. But you want to find what this thickness is at some value of the strain, not the stress. Well, so I want you to recognize that you can put all this stuff in the matrix, but you don't always have to know everything that goes into that matrix to get some useful values out. Like remember the relationship between a shear stress and a shear strain is that shear strain is equal to 2 times 1 plus nu over E times the shear stress. And you can see that if you just look at how the matrix multiplication works. And so this is going to be 2 times 1 plus nu over E times whatever that function was that you had before. And then that gives you your relationship. Any other questions on that one? Or okay. All right, well, let's talk about internal loads when you have distributed loads. Okay, so if your beam has distributed loads on it, before you can do a calculation, you always have to represent the distributed load as an equipolant point load. So we're always going to represent the distributed load as a point. It's always going to be a force, I guess. We're never going to have distributed couples or anything. When can you, okay, so when do you represent the distributed load as a point force? Remember that you can only do that once you've chosen the body to isolate, okay? So like, for example, when you isolate the whole beam with a distributed load, in order to calculate the external loads, you treat the distributed load as a point force, like wherever it is, okay? But then when you go to the cuts, you can't keep that old point load. You have a new cut, you've chosen a new body to isolate, so now you have to redo the process of representing your distributed load as a point force. Okay, so represent the distributed load as a point force once you choose the body, or the part of the body to isolate. If you do it before you've chosen the body, you're going to get wrong answers. And remember that the magnitude of that point force is the area of the distributed load shape And the location of the point force and really all we care about is the x location. The y location doesn't affect anything. The x location is the, the x coordinate of the centroid of the distributed load shape. Okay, so I'm just going to go right into an example with this. So let's say we have a beam that's cantilevered over here, and the distributed load shape is triangular. With a maximum value of 10,000 newtons per meter. That's 1,000. And the length is 3 meters. And we want to calculate the internal loads. So the first thing we're going to do is isolate the whole thing to calculate the reactions at the wall. There are no torques about the long axis of this beam, so I'm just going to leave torques off. All the internal torques are going to end up being 0. If you wanted to calculate it, you could, and you would just get 0 for everything. Okay, so here is our isolated piece. So here we have a force RA, and we have a couple. I'll call that MA, reaction couple. And then we have the distributed load. Now that we've chosen a body to isolate, we can represent this distributed load as a point force, and we're going to do it by thinking about this triangular shape. Okay. This has a length of 3 and a height of 10,000, not drawn to scale. Okay. So where is this centroid located along X?
Third from the right.
Yep, a third from the right. So this distance is a third of 3, which is 1, which means that if you're going from this side, this distance is going to be 2. And the area is 3 times 10,000 over 2, just the area of a triangle. And so that's 15,000. So we have a downward force of 15,000. And this distance is 2 meters. So Newton's second law says RAX, RAY plus 0, negative 15,000 is equal to zeros. And so RA as a vector is 0, positive 15,000. And now the moment equation about the z-axis with the about point here. RA doesn't produce a moment, but that couple, it doesn't matter where that couple's applied. So even though that's acting at the about point, that's still going to produce a moment of MA. And then we have a clockwise moment. So minus 2 times 15,000 is equal to 0. So MA is equal to positive 30,000. Any questions about getting the external loads? All right, so our complete free body diagram now looks like this. We only have an upward force, so I guess I'll... So we have an upward force of 15,000 newtons. And a couple of 30,000 Newton meters. And then a distributed load with a magnitude of 10,000 newtons per meter at the right end. Okay, so now we have to figure out how many cuts to make. Here are the two endpoints. And now we're looking for any place where there are point forces applied, point loads applied of any kind, so point couples or point forces, or places where the distributed load function changes. This distributed load function is the same the whole way. And this function, like if you're representing this distributed load as a function, notice that the height of this distributed load is going to be a line, and it's represented by the function y equals, we could do it rise over run, so this would be 33, or 3333.3 repeating times x. And we can think of this as our downward distributed load Q. That's the Q. Okay, so how many cuts do we have to make? N is equal to 2. So we just need 1 cut for this whole thing. And so our cut 1 is going to be valid for all the x's, 0 to 3. So it's going to include some but not all of this beam. But here is the thing that makes this tricky. That means that not all of the distributed load is going to be included. Okay? So the height of this distributed load is not going to be 10,000 on the right end. Since the length of this thing is x, the height at the end of the cut is equal to that Q function, which is 3333.3x. Okay? And so this is setting up a triangle like this that has a length of x a height of 3333.3 x. That means that to get to the centroid, we're going to go a distance of, it's 2/3 x to go from the right side to that centroid. It's 1/3 of x to go from the right end to the centroid. So to go from the left end, this is going to be 2/3 x. And the area is base times height over 2. And so that is 1666.6 x squared. So that's what we're going to use as our point force of this, representing this distributed load. Okay, so cut 1. For x's between 0 and 3. So here's our cut. We have the upward force of 15,000. And a couple of 30,000. And then the distributed load, now that we've chosen the body to isolate, we can represent this by the point force. And this distance is 2x over 3. And then we have the internal loads. Any questions about that free body diagram? So Newton's second law. Yeah.
X squared.
Yes, thank you. So Newton's second law says 0, 15,000 plus 0. Now these can get confusing, but remember, this is the way to make sense out of the signs of the vector components, okay? So what you always want, the way you always want to think about this is you have a unit vector in the direction of the drawn arrow, okay? And you're multiplying it by this value. So if this value comes out negative, it flips the direction of the arrow. So in this case, since the arrow is down, that's a unit vector of 0, -1. Multiply 0, -1 times this. And you get a force vector of -1666.6 repeating x squared. Plus t negative v is equal to zeros. So there's no internal tension. And the internal shear force is -1666.6 repeating x squared plus 15,000. And now the bending moment. The about point is here. So the 15,000 doesn't produce a moment. the positive 30,000 is in there. Then we have a clockwise moment with a moment arm of 2x over 3 and a force of 1666.6 repeating x squared. And then plus m minus Vx is equal to 0. Okay, so m is equal to Vx plus, this comes out to be 1111.1 repeating x cubed minus 30,000. And so m is equal to negative 1, plug in v for the v here, and multiply it by x. So negative 1666.6 repeating x cubed plus 15,000 x plus 1111.1 repeating x cubed minus 30,000. And so m is equal, let me talk to him. So m is equal to negative 555.5 repeating x cubed plus 15,000 x minus 30,000. Any questions about that? Yeah.
Yeah, so why is the 1666.6 repeating x, why isn't that x squared again?
It was x squared for v, but remember we're multiplying v times x.
Okay, gotcha.
Yeah, so remember that x isn't a subscript or anything. That's like we're multiplying v times x.
Yeah. Okay, that makes sense.
And, okay, remember the derivative relationships. You can use this to check your work. dm dx has to be equal to v. And negative dv dx has to be equal to q. So let's check those real quick. dm dx is negative 1666.6 x squared. So that term works. dm dx, the derivative of the second term is 15,000. That matches. So that first derivative relationship holds. Then the second one, dv dx, negative dv dx is positive positive 33333x plus 0, and that matches our q. Yeah.
So from here on out, are we going to be considering the weight of the beam as the shape of it? Should distribute load all the way across it?
Yeah, so since our beams are always going to be the same thickness the whole way, distributed load is just a uniform, a weight is just a uniform distributed load that's equal to the total weight divided by the length. Any other questions? Okay. See you later.